Hello everyone, thank you for joining and watching my YouTube video. My name's Adam McMurchie, and last week, or earlier on in the week, I made a promise or a pledge. I said, if anyone's interested, I'm going to live stream a video of me building an AI, which can build an AI, which can build an AI, and so on and so forth, right? So I got quite a good, nice bit of feedback from that, and hence the shirt that I'm wearing today, because some of the feedback was quite hesitant. And so really just to say, like, I've done it, and this video is going to be me showing you it actually working. But there's quite a few caveats, right? Because it's quite complex, and what I want to do is I still want it to be for a full audience. I don't want it to be just for ML engineers or DevOps engineers. So I'm going to split the video into 3 parts, right? So the first part, this part, is I'm going to talk through some of the theories. You'll see some cute pictures, and then I'm going to show you it working in this part, right? So I'll show you the end product and show you the theory. Second video is I'm going to build it from scratch. So I built it already. The second video is I'm going to build it from memory and just some notes that I made, right? So I'm not going to cheat. All I'm going to do is I just wrote down here some basic functions to remember, and so there's nothing special there. So I'll rebuild it from memory. And then the third video is depending on demand, right? Because what I've built is I built the core engine, right? So the engine is an AI code generator, right? The third part is this part which you won't see today, which is it creating an intelligent baby, right? At the moment, what it does is it generates sophisticated code, right? Depending on how long you run it. So it creates millions of lines of code, which I don't know because it generates it randomly with evolution, right? So the whole point is it's generating code which works and compiles, right? So it's not just random fluff, it's random fluff which works. But then the final step would be this element of it generating AI. So each baby that it creates would be a fully fledged and like in its own right machine learning model, algorithm, or whatever. Now that final part is monotonous, right? So it's not that the reason I've not done it now is it would take a little bit more effort, like a couple more days of development. And I'm only going to do that if you want me to do that. So if I get more than 5 people saying I want to see that final cherry on the cake, I'll do it. But even if I don't do it, by the end of this video, you'll see how to do it, right? Because it's not that much of a stretch. Okay, so I appreciate that's a lot. That's me explained it in maybe a bit too much detail, but like I said, I've tried to rehearse how I'm going to explain this a few times. It's a little bit involved, but not that involved. There's a few more caveats I'll need to add. Again, going with the Terminator theme, because that was the most popular responses which I got, which is both like kind of morbidly satisfying, but also don't need to worry about it, because I doubt it would be that sophisticated unless I maybe ran it on the cloud, who knows, for a very, very, very long time. But the other point I want to get across is that the what I'm going to show you today is not the full final finished product. So I don't want people coming to me and saying things like, oh, well, why aren't you running it, threading it on multiple cores and things like that, right? It's like, I know, right? So if you're an ML engineer, DevOps engineer, believe you me, what you see is a potential flaw. It's all the flaws that I see. But rapid prototyping is an art, and if you spend all your time trying to build the ultimate framework running in containerization and multiple threaded and things, you just won't get anything artistic done. So this is me showing you like the core function feature working, right? Later on, if I wanted to ship this, then I'm going to build it, encrypt it, keep it secure, things like that. Another part, again, is quite negative, but I don't mean to sound negative, is I'm not sharing the code, right? So in my second video, you'll see me build it, so you'll kind of get it anyway, but I'm not sharing my code because my code is a much more sophisticated version, and who knows, I might use that one day for something. but that I'm not hoarding, right? So I don't believe in hoarding. So that's why I'll also show you me building it, so you'll know how to build it yourself. The only difference is the stuff that I'm not showing you is just me investing a lot more effort of my time. But you'll understand all the core basics. So we'll talk about the theory just a tiny bit, and then it's like this slide and another slide, and then I'll show you the code. So high level again, this is just for people full backgrounds. The way it works is I kind of have this generator, right? So it generates sophisticated code. For those who know a bit more about tech, then it's just generating random Python files, right? And those Python files could be, I can set my initial seed to say 5,000 or 5 million or 500,000, and then they go through a stage of genetic selection. So let's see if when I mean selection, what I mean is there's a quality function which will only say take the top 10%, top 5%, which I define, and those top 5% survivors, you could, if you're good at biology, you can think of that as just like the world, right? Evolutional application on biological life forms, right? Not everybody makes it to adolescence and reproduction, and so the small percent which do make it, mummies and daddies, they'll have kids, right? And we're not restricted to biology here, so we can be a bit more sophisticated with AI. We don't need to just donate DNA from mum and dad. We can donate DNA from 50 mums and 50 dads, or only 5 dads or whatever, or only we could donate 10% from mum and 90% from dad, or 90% from mum and 20% from 4 other dads. So think of these as things which I can tweak, right? If you're an omnipotent being and this is my world, these are parameters that I can tweak, and not too dissimilar from hyperparameters. And you can have other kind of babies which are mutations. So it might be the same clone of a baby, but with additional DNA added. Additional code added, shall we say, and it could be some of the codes removed, or some of codes kind of mixed and jumbled, or it could just be the exact same baby but with additional lines of code added. Now, once you see me run this, you'll say, well, wait a minute, how come your final ones which finally made it to the end, how come there's not many mutated ones? Isn't mutation what makes us us? And it's like, well, yes, it is. But additionally, one thing, just like in biology, is not all mutations are good. In fact, most mutations are either negligible or even detrimental. If this doesn't make sense, then the best way to think of it is essentially I'm generating code which then merges with other forms of code which have been generated, and they're just jumbles of lots of code which continually go through a process of you think of me just cutting the top of the cream, right? So I'm taking only the top 5% each time. So each time I'm getting the best and breeding them to make even better future generations, right? And so this process just continues in a loop. So that's essentially what I'm doing. And I'm not going to go into any a bit more. I'm actually going to show you it working now, and then I'll do a bit more talking after that. Okay, so this is the app. This is like 50 or 100 lines of code for the front end to make it cute. So the actual original program which I built didn't have an interface. It wasn't cute. It was just things that I was just changing in the lines of code, but I decided to make it pretty so I can talk you through how it works and what we can do. So essentially, we've got 2 things we can do. Right? So we can execute it and start the process of breeding and selection and so on. And then once that's finished, it'll create all of these bots or AI and into 10 folders, right? Because I'm only going to do 10 generations max for this demo. And each one I can then just evaluate. So I click this evaluate, which just lets me see what that code looks like. So that's it really. So we have an execution stage where we create them, and then an evaluation, so we can then evaluate all the babies that were created. Some more caveats, I say caveats, just more things, is think of these as knobs which I can twaddle, right? And I can adjust, right? And they'll adjust the complex. These can change how sophisticated the generation of the babies are. It can also change how long this will run. So I've actually got a £3,000, $4,000 MacBook, so it should run quite fast. I've capped it at 500,000 initial seed. So this is like the seed population. I can make it more if I want, but I'm not going to. So for this to run while you're here, probably I'm just going to kind of cap it, say something like 10,000, right? Just something that's doable, that'll just run. In fact, I might even make it less. The reason why I'm making it less is because the higher up the scale this goes, the more iterations that the processor needs to make, and the longer you're going to have to sit here listening to me talking while it runs. So I'll just talk you through each knob. So this is just saying, like, because we're essentially generating code, we could say what's the minimum length of that code, right? So this is like the sophistication, if you think. Again, just for your purposes, I've limited it to say 0 and 8, but I'm going to bring it down and just say, maybe 4 lines, 1 to 4 lines, right? So you get with that, you get like a for loop. You could probably get a function. Maybe, yeah. So I might just say move that up to 2, because at least, yeah. So bring it to 2 and then bring it down to 4. So that's just me limiting the random variations of what the width and width of the code can be. And this is just the height of the code. So again, I can make this longer, right? So if I was doing this in a real simulation, I would probably make the maximum numbers maybe infinite or close to that, because I want to see what maximum complexity I can get and run it on the cloud. But for your purposes, I'm just going to squeeze it down just to show you. So I'll say I want a minimum number of 2 lines of code. Maybe just max it at 4. That should be fine. 4 or 5. 5. Just keep it 5. I want it to be too stupid. This is just like complexity. So this is just I haven't worded this properly, but it just means complexity. It's you think of these as like the 4 declarations, definition classes. I've just created my own quality metric. This is for anybody that knows AI, genetic algorithms very well. This is just your selection function, parity selection function, which I've tailored. So I just keep it 1 for now. If you have lots of really high, if you have like a really high volume simulation, which you could do in this, is you probably want the parents to contribute less of their DNA, because you're going to get more. But because in this case, I'm only going to have 5,000 iterations for the initial seed, plus the generations, I'm going to have more sparse data. So I probably want to see more parent DNA. Like this is actually the probability. I should really change this, right? So it just means I've got a loop where I say, for each line of code, what is the probable chance that line of code of the parent will be passed on to the child? And I kind of got the same again with mutation percentage. For mutation, you always want it high, in my opinion, because I just want to inject more randomness. And then this baby multiplier is essentially, all I'm saying is if there's a number of survivors, say there's only 20 survivors, then they'll have 20 times 200 babies in that case. But I'll just maybe make it 20 times 150 babies. That just allows me to kind of narrow the bottleneck of populations, right? Because sometimes what you want is sometimes you want a narrow bottleneck, but huge percentage of children. I'll talk about that once it's training and explain a bit more. And then number of evolved generations, I'll just set to 10. So I just want 10 birthing steps, if you can think, or 10 ancestors of generations. The advanced options I want to explain, there's just some more bits and bobs I added into that for me. So I've got the code running now, and I'll talk while it's running. Hopefully it won't take too long. But let's go back to this sort of bottleneck idea, right? So I'm no biological expert, certainly not. But my understanding is there are certain theories, particularly in regards to human diversity. One of them is something along the lines of there was a cataclysmic event, I don't know, 80,000 years ago, somewhere near Indonesia, which was it's hotly disputed in history. So it's actually a disputed history if it actually happened or not. But the proposition is that this cataclysmic event wiped out the majority of humanity and brought us down to under 100,000, let's say 20,000, right? So could you imagine only 20,000 humans living on the planet? Now, I'm not sure if that's true or not, but it led to a line of thinking in evolution where the bottleneck was restricted to one place on Earth or a very sparse population. And after that event, it actually triggered, we had this very sparse, not diverse survivors. And that cataclysmic event caused us to spread out again even further, and kind of you have this if you know much about sort of rocket engines and thrust, or or anything, sort of gas physics, if you constrain something, or even in psychology, repression, right? So if you repress an emotion, then the reaction is this, it's almost an outfanning. So if you imagine this huge population of humans get pushed through a bottleneck, and then once that bottleneck, the volcano's passed, the reaction is this massive spreading and a huge diversity. And this is something which we can actually see in the code as well. So yeah, it's a bit of a ramble. I wanted to get that in before my code finished training. So this is just some info that I've got, and we'll just drill into it, right? So I click on evaluate, and then let's have a look at the seed code. So there was a lot of seed. Oh, actually, only 2 survivors made it. Oh no, sorry, I didn't order them. Yeah, that's my fault. I didn't order them because it's the random distribution. So we got what, like 1, 2, 3, 4, 5, 5 pieces of code actually made the initial. So of the 5,000 that I created, only 5 of them were code which compiled, and they're not very sophisticated. So we've got a random int generator, some variable assigned to array, some more random integers. Nothing particularly complex here, which is not filling me with hope. But that's fine, because we only did a few 5,000 iterations, right? But the point is it still produced babies which actually worked, right? Then we can look at the generation. So let's drill down to the second generation. What did they look like? I'm not, this isn't a table, so you won't see indentation and formatting things. So let's just jump over to the actual file structure and have a look. So let's go to my one, and so let's have a look at what what I predict is that each successive generation will be more sophisticated than the parents, because we're just chopping that top 5% each time, and also because the parents weren't that smart to begin with, we hope that more mutations will make it through the cut. So again, these are the parents, just a couple of lines of code. And then we can look at, so this, we multiply them. So you can see straight away that we've got a little bit more lines of code. You can see I also put a tag to say mutated. So something else happened here. A variable 3 was added in with a comma, maybe some other lines of code. So you can see in the first generation, we've got a few mutations already. Now, just me setting that mutation to 80% doesn't guarantee a lot of mutations will come in. You can see not a lot of these actually made it, because again, not all mutations are useful. But hopefully, if you imagine running this in the cloud with much more lines, what you would see is with large volumes, mutations would seep in, right? Because mutations, these beneficial mutations, they play on the edge cases, right? It's the small numbers which then contribute to complexity over time. So you can see, now we are getting more lines of code here, right? We're getting more mutations, And so if we go to number 10, which jump to the end, now we can see, okay, something is a little bit more interesting. Now, okay, you might say, okay, Adam, that'll compile, but it's not very complex. Like, well, yeah, because one, we ran it for a very short time and a very, we really restricted the diversity of length and breadth of the column. We also restricted, which I didn't show you, but I restricted the tokens, which I'll allow, because I just didn't want to create anything dangerous while I'm running this demo, because actually it leads me to this kind of a problem. But you see now we've got code which are quite interesting. We've created more code, and I can actually, I'll verify this works, right? It's just so people don't know I'm bluffing, right? So let me open up a new terminal. So I'm gonna cd into my folder. And I'll cd into the 10th generation, right? And try to run a random one of these. So I'll go Python this, and I'll just let's go. That 238 is looking at me, so we'll go for that. And nothing happened. I'm not surprised, because this is essentially code that just compiles, right? So, or maybe something did happen, but I doubt it, right? So this is just random lines of code which just happened to pass a compiler and run. And the reason why you're not getting anything surprisingly pretty, again, we are getting some form of complexity that's coming out of here. It's just not the complexity that you would imagine that, when I sort of put it in the LinkedIn tweet. And that's just simply because, think of this like, this is a genetic algorithm, right? And think of this as, can 100 monkeys in a room type the full manuscript of Beethoven? And of course, yes, it can, given infinite time. Now, you're saying, you might say, well, Adam, we don't have infinite time, but that's where we tweak quality metric, all of those parameters, right? It's how we're essentially guiding evolution, right? So what have we learned from this? So it's possible, an ML genetic algorithm, machine learning algorithm, or AI, can generate code, and it can generate sophisticated code. And the level of sophistication is limited only by the computational power that you've got, and the fitness function. And the fitness function is where the magic comes in. The fitness function, when applied to that, is what shapes the evolution. So for me, in this case, I could say the fitness function is, do you compile? That's one. So think of this as the evolutional threshold that you need to pass in order to have babies. Is your lines of code syntactically correct? Do you actually do something, right? So this is where I could add more sophistication in the fitness function. So I could say, I want you specifically to do things with files, or I want you to be malicious. And just for an example, I could say, I want to only allow the ones to pass which are able to do some form of network penetration, or file corruption, or something like that, right? This is where I tie in the final step, which be in the third video, depending on if you want to see it or not, is the genetic algorithm is essentially the framework which allows things to be shaped in their progression of sophistication. Now, if I want to then apply this to AI, so to swap, all I need to do is swap this function. So this function I've got written down here, which is a code generator, right? So in this string of code, there is somewhere in my solution, it's a function which just generates the random code for the seed values, right? So this part, all I do is I just swap out this part to generate random AI. Now, you might say, oh, only, it's not that hard, right? So I could easily just scour GitHub for a million AI models, from the most amateur stuff on Kaggle to more sophisticated stuff, all the open source stuff, and save it into an S3 bucket, and then use those as the seed values for this, right? So it's not that much difficult, right? So then you're trying to visualize that and you're saying, well, so what's happening, Adam, is it's actually just mixing lines of code. Well, yeah, again, so I could then change that based on the fitness function. So I could then say how I want these two different AI to breed and create baby AI, right? So the only thing is to really just lift out the iteration step and tweak the quality functions. But to do that, take another 2 days of my time. And so I'm only going to do that if you want to see that. I'd like to do it. I probably will do it, but to do a YouTube video takes time. And so that's where we are, right? So I appreciate, I kind of covered a lot and ranted a lot as well. So I may need to post-edit this video, or I may just ship it as it is, because if you've got to this point, then thank you very much. So those are the functions. So this is what the original code was. So the original code was I had a code generator. So some function that generates random code, does a few checks to make sure it's fine. Then I had a quality function. This is your fitness function. The selection function is essentially just, it's rank ordering all of the survivors or the kids and then selecting the top 5%. The next part is the breeding function, right, which is, we have many different ways you can breed them, right? So you can just breed, we could make it monogamous parents, or we can make multiple parents. We could contribute in different ways. And then finally, this is this optional generation function. So if you want to do this at home, if you can get to this point, brilliant. But this part is just where I'm essentially wrapping all of this in a loop and looping round for as many generations as I want. But each loop I'm generating files, and there's a lot of throughput. So you might not want to do that if it's just on your own computer. That's not really high spec. But that's the core functionality. I'll jump back to me. Your screen sharing, stop sharing. So that's hopefully been able to share with you the basic concepts of how this works. You understand and see what it does. Realize it's maybe not that hard, but probably does take a bit of work for anyone, not just me. And if you are interested, I will continue, and I'll do so the second video is where you'll see me build this from scratch, and then the third video is where I'll apply it to AI, which could then so I'll apply it to AI models, which could then do the same again. So that's it really. Just a sort of big thanks to everybody that sort of stayed this far on the video. This was everything I did from my own top of my head. It's all my own written code. There's no ML libraries, so you can do it yourself. If you are a decent coder like me, then I challenge you to just do it without watching my next video and see how far you can get. Just remember those core functions, right? Generate code, check the fitness, breed the babies, and loop it around again. Thank you everyone for hanging on and watching this. I look forward to your comments, and if you want to know any more, drop me a DM, and we'll continue the video in the next session.